Okay, this video is on the fundamental theorem of algebra. This is a theorem that sounds scary and really intense, but really it just tells you something very straightforward and very simple. It helps us when we're trying to find all solutions of a polynomial function. So the fundamental theorem of algebra simply states that the degree of the polynomial is the same or equal to the total number of roots of a polynomial. So first, we just need to remember that the degree is either one of two things. If you're in standard form, then the degree is the highest exponent of our polynomial. And if we're in factored form, then it's the sum of all the exponents. Now, if we're in factored form, we don't really need to do much work to figure out all the solutions. We can just get them all by setting all of the factors equal to 0 and solving for the roots. If we're in standard form, that's really where this is going to come into play. Now, what I mean by that is this. Polynomials can have real and they can have complex roots. So real roots correspond with x-intercepts, and complex roots are not visible on a graph. So if I have a polynomial function, I put the equation into my calculator and I graph it. And when I do that, I see x-intercepts. The number of x-intercepts, including multiplicity, tell me the number of real roots. If the degree of the polynomial is higher than the number of real roots, then I know that I have some complex zeros. I can find those by using division, long division, or synthetic division to find the remaining factor or factors of the polynomial. And then we're going to take whatever's left, and we're going to either use square roots or the quadratic formula to solve that quadratic. It's usually going to be quadratic, to find the remaining complex solutions. So here's what I mean. So how many total roots does y equals x to the fourth plus x cubed plus 2x squared plus 4x minus 8 have? Now, when I'm talking about this, what I really want to know is what's the degree of this polynomial. So right here, that 4 is telling me that this guy has 4 total roots. That's all that I can say at this point without a calculator. I went to my calculator and I entered this whole thing in and I hit graph and it gave me this picture here. So just in terms of what the scale is so that you know, this is -1, this is -2, this is 1, this is 2. These are all counting up by ones. So the next follow-up questions are how many roots are real and how many of these 4 roots are complex. So when I look at my graph, I see 2 x-intercepts. So that means, 2 x-intercepts implies that I have 2 real roots. Both of those roots, I see that the function goes straight through. So each of those roots only has multiplicity 1. So my 2 real roots are x equals -2 and x equals +1. And I see those are the x-intercept values. What that means is that since there are 4 total, and I know that 2 of them are real, that means that I have 2 left that are complex, so imaginary. So they have units of I in them as their answer. What are they? This is where division comes into play. I'm going to personally choose to use synthetic division because it's faster. So up here, in order to do synthetic division, I need to think about what my coefficients are. So I'm going to put 1s in those places just to remind myself that that's what's going on there. So in synthetic division, we start with our box, and in that box we put the root. So I'm going to start with a -2. You could start with a +1. We're actually going to do this twice. Pick either one first. I just picked the one on the left. Next to that box, I put the coefficients from my polynomial. So here a 1, a 1, a +2, a +4, and a -8. I leave a space and I draw a line. The first number, the first coefficient, always comes down underneath the line. And then from there, I'm going to do the root. I'm going to multiply. And then my results goes up there. So that means -2 times 1 is -2. -2 goes above the line. Numbers above the line are going to get added together. So 1 plus -2 is -1. Numbers under the line get multiplied. So negative 2 times negative 1 is positive 2. Numbers above the line get added. 2 plus 2 is 4. Under, multiply, negative 8. Over, add. 4 plus negative 8 is negative 4. Under, multiply, negative 2 times negative 4 is positive 8. Above, add. Negative 8 plus 8 is 0. I'm done. Now, this last number would be the remainder. It should be 0 here because I know that this is a factor. Okay. Now, here's something interesting. Our starting function, polynomial, was degree 4. We divided out in x. So this resultant here is degree 3. Okay. So now I'm going to erase this notation right here, if that's okay, because I need this space. So let me do a little erasing here. Okay. So I'm going to come back now. Now the reason I want to come back is because I actually have a second root right here that I also can factor out or divide out. I'm not really factoring here, I'm dividing. So I'm going to put another box next to this list of coefficients, and I'm going to put my second root there. So I'm going to put the root of x equals 1 there. And I'm going to do the same process again, taking out the second root. So the first number gets pulled underneath the line. Numbers underneath get multiplied. So 1 times 1 is 1. Add up and down, that's 0. 1 times 0 is 0. Add up and down, I get 4. 1 times 4 is 4. Add up and down, I get 0. Again, that last number is my remainder. And then I always have to stop and think, this one was degree 4, this is degree 3. I took out one more x, so this is degree 2. Why is that useful? It's useful because these are the coefficients of a degree 2 polynomial. So that means this is a 1x squared, this is a 0x, and this is a plus 4. So I can now rewrite this. This is my remaining polynomial. So I now know that x squared plus 4 is what is remaining, and I want to know when does that equal 0. This guy right here is going to give me my 2 complex roots that I'm looking for. So I need to solve this equation in order to figure out these 2 complex roots. This is a real simple quadratic. There's no linear term, so I'm going to choose to solve this by square rooting. So I get x squared equals negative 4. If I now square root both sides of my equation, I remember that when I square root both sides, I'm going to undo that there. Let me move it over so I ran out of space. When I square root both sides, I get a plus or minus every time. So 2 answers coming out of here. And the square root of a negative gives me an I. And the square root of 4 gives me a 2. So my 4 total roots of this polynomial are x equals this negative 2. X equals positive 1, x equals 2i, and x equals negative 2i. And that's how I can use the fundamental theorem of algebra to find all of the roots of a polynomial.